Morning, everybody. Thank you for attending this session, this RBB Lunch and Learn session here today on looking at the Internet of Things in a high mix, low volume world. We're all familiar with, of course, a lot of the high volume, low mix world that we're surrounded with every day, things like our Fitbits and smart homes and things like that. The things that characterize a lot of these kinds of applications, obviously, in addition to the sheer volume and ubiquity of it. But I think the other thing that is important, and we'll see about this a little later on, is those applications tend to be configured versus programmable. So today, again, we'll talk about the high mix, low volume world. And in particular, we want to talk a little bit about planning, initiating such a program, and managing applications in this space. So if you want to switch to the first chart there. All right. So first of all, before we get going, we looked at the attendee list, and again, very thankful for the group that we have here today. And we noticed that a lot of the backgrounds, very exciting to us, of the people in the audience today tend to be from an IT side of things. And one of the biggest things in our industry that's been occurring over, obviously the last several years is the convergence of IT and OT, operational technology. And if you go back quite some time, it's been a continuing quest in terms of the IT group to be able to sort of reach down and grab meaningful data out of the enterprise or the system that can actually be consequential in decision making. So it's important to get real-time, fresh data. And there's often been this divide between IT and OT. So that's what IoT is doing for us. So first of all, let's define how is high mix, low volume different from small batch? Because RBB specializes in small batch, and that's a specialized form of high mix, low volume. A typical high mix, low volume business would involve something that sets up a line and runs product maybe for weeks or months of a particular configuration, either ships that out directly or puts it in inventory, and then has a line changeover and then runs another product for a period of time. RBB is much more flexible than that. The quantities can be as simple as 1 unit or 1 unit a week or 100. And that's what's important. That's one of the key differences between a typical high mix, low volume and what RBB specializes in. So all the concepts we'll be talking about here today are really applicable to this small batch world. One of the things in selecting the topic here today that we thought about is there have been just a number of sessions out there in the IoT world extolling the virtues and the benefits of IoT. And I'm sure you've all heard them over and over again. Probably makes sense to just in summary say why is it people are chasing IoT? Well, you can predict impending failure of a system. You can increase safety. You increase efficiencies in integration and all of those things. So we're not going to really focus on those kinds of elements today because we think that those have been covered quite a bit in other sessions. We think that this session today is particularly relevant because the threshold, if you will, the bar of being able to get involved in an IoT program is lower now than ever before. Even going back just a few years ago, if you wanted to roll out an IoT program, it was clear that it was going to require perhaps many years, or at least 1 or 2 years, and perhaps millions of dollars. But because of a number of positive things that have been happening in the industry with standards and other positive things that are occurring, it's dropped that threshold down where others can participate in it. Our objectives here in this session are first to identify some of the unique aspects of high mix, low volume IoT systems. Secondly, to review the factors that drive the decision-making around each of those elements and how to manage them. And then lastly, we'll talk through a little checklist, a little process checklist about how you can initiate this type of an IoT program. So high mix, low volume IoT deployments. Let's talk about what sets up these kinds of opportunities, because again, we're not talking about selling something at a big box retailer or whatever into a consumer market. We're talking about something much smaller and more specialized than that. So there are end user systems out there. That might be a manufacturing plant, small, like a Ford Motor Company or something. Oftentimes what comes out of the situations in end user accounts is somebody identifies the need to be able to have data from one place sent to another place to affect decision making or to close the loop on a control process or whatever. And so these oftentimes get referred to as a one-off, kind of a one-off system. You'll probably never build another one, but it's the one that gets designed and built for that particular purpose. And then just tends to get supported and maintained over time until it gets dismantled and replaced by something else. Alternatively, sometimes one-offs are replicated over time. So if you take that same auto manufacturer that we were referring to, there might be a system in place for air quality monitoring. Say it's a paint booth where you're monitoring VOCs, volatile organic compounds, and it might be proven out in a particular facility or shop and perfected in that, and then that system gets replicated either within that facility or across multiple manufacturing plants. But again, even if it gets replicated, these deployments still tend to look, they're not volume manufacturing where you're setting up a machine and letting it run for weeks and weeks compared to typically what you think of in manufacturing. There's another category of products that fall into this high mix, low volume IoT deployments, and that's OEMs, original equipment manufacturers. Oftentimes we see in this space might have a business need to go back and retrofit equipment that they have shipped a long time ago. So that equipment in the field might have some kind of an analog output or a series of digital outputs on it that either right now are not being used at all or they aren't connected to anything. A typical example of that kind of a situation is most providers of equipment include some kind of a serial port on the equipment. Might be an RS-485 serial port. Those were typically, they would be put in maybe during a test, development and test. They might be used in manufacturing. Oftentimes, once the equipment shipped to the field, those serial ports they often don't get used. So sometimes we see a lot of OEMs that are going out and saying, hey, I can derive new revenue from products that I have shipped a long time ago if I come up with a field kit, retrofit those systems, and then start to enable the flow of data, which may allow them to charge more for their equipment or set up other revenue opportunities such as warranty enforcement or other things. OEM products also that fall into the high mix, low volume realm are things that it might be a limited offering. So say a manufacturer has a product line and most of that product line might not benefit from monitoring or there's no electronics in it or whatever. So an OEM may make a decision that says, the very top of the line product that we ship here is going to have some kind of an IoT or a monitoring capability. So here again, there's another sort of high mix, low volume opportunity. So they can fall in both end user systems and OEM products. Additionally, system integrators are are usually out running around factories and in commercial buildings and things like that, trying to find a way to increase efficiencies and for the overall operation. And that will oftentimes set up needs for a high mix, low volume manufacturing program. So if we go to this next chart, it's an eye chart, and it's kind of specifically put in there for that reason. This is a chart that you can find out on the internet if you're interested in looking at it yourself. It's a Matt Turk IoT landscape chart. There's 900 and some logos, I think, on this chart. And the reason I put this up there is it just illustrates the complexity of the IoT business. So while there's, you know, all these exciting aspects and benefits of IoT, that knife cuts both ways, so to speak. It's still very much a fragmented industry. So within this landscape chart, you'll see that there are a number of providers that are listed that provide infrastructure components or connectivity or software, horizontal software platforms, security packages, big data analytics packages. You know, you generate all this data, then you have to be able to, rather than just let it hit the floor, there's a need to take that data and turn it into actionable business information that's valuable. There's gateways on this chart, communication gateways going from sensor systems up to IT systems and such. There are microcontroller providers, there are sensor providers. So it gives you an idea of just how complicated the whole ecosystem can be. So let's abstract it up to a little higher level here so that we don't have to look at 900 logos and put our eyeglasses on. The typical elements of an IoT system are illustrated in this graphic. And obviously every program can be a little different. Some might have extra elements, some might drop some of these off, but let's just kind of talk through some of these. First, of course, is some kind of a business application. Presumably the reason you built the system was to do something with it. So it's usually best to kind of understand that element first. Although we all know, just from practical experience, that sometimes systems get developed completely the opposite way. They grow from the bottom up as opposed to being architected and designed from the top down. So there's business applications, of course, that need to be part of an IoT system. And going around all of that, you have some kind of a user experience and whatever that needs to be understood. Typically these days, there are mobile apps that are associated with the system. Sometimes these mobile apps access the IoT system across the cloud. Sometimes using today's technology, they're able to access the devices or equipment directly over low-cost wireless communications like Bluetooth Low Energy, which most people have in their phone, of course. There are I/O modules, input-output modules, typically in a system. You know, usually these systems have to be driven by some kind of real-time data. So these might be, you know, pressure sensors, proximity detectors, you know, valve actuators. They can be a number of different things, but typically there's going to be some kind of input-output associated with the system. And then a lot of times architecturally, it makes sense to, of course, bring these back to some kind of a hub or a communications gateway where all the disparate sensor and actuator data can be brought into a single communications engine, if you will, where there's either value-added processing or complex control logic or something that gets implemented there. There's also, of course, cloud software that's oftentimes involved in this, and that cloud software can be used in a number of different ways. It can be used operationally, so you can look across facilities, but it can also be used for maintenance of the system. For instance, setting up and managing over-the-air transfers of new firmware to devices that are in the field. So it's not enough just to have all these elements, the the apps, the cloud software, and everything else. You could go out and buy all that stuff and throw it on the table, so to speak, and it wouldn't work together. So it's important for all of these elements to work together is to take a systems engineering approach, and we'll talk a little bit more about that in a moment. So all of those elements get wrapped in a systems-oriented approach, and then program management goes all around that to make sure that you're not just trying to put together these pieces and not achieve the desired results. Next chart. So one of the things to keep in mind, most of you are probably familiar with, a life cycle analysis, a life cycle view on whether you work on hardware, software, IT, whatever. There's a life cycle perspective around each of these things. So if you think about all the elements that we just talked about, each of those have their own little 9 steps associated with this. So you need to do some analysis to select that component and planning, and typically there will be some design and development to make that part of the system. There will be testing that needs to be done before those get deployed. And then we all know once something gets deployed in the field, it's like anything, it needs to be maintained. And so there's that maintenance step. And then eventually there's some evaluation that goes on, and then a disposal of that particular element. So it's critical to understand that there is a life cycle, and each element of this system has a life cycle. And if that isn't understood, then it becomes very difficult to make all the parts work together, or to even make the right choices about, gee, should I make this or should I buy it? Because in any of these kinds of systems, it doesn't matter how large your organization is, it will become very clear very quickly as you look at these elements that there are certain wheels that you might not want to recreate. It's a lot easier just to go out and procure those. Okay, this next chart I think is something that it's probably obvious to most of us, but it's worth talking about here. Is there's an inherent relationship between how much non-recurring engineering cost is spent on an item and what the recurring, or what the bill of material or product cost is when you're done. So there's just a bunch of fictitious numbers on this page for illustrating the purpose. But let's just say, for instance, we had a certain system or product requirement, and if you went to a catalog and said, well, we're not going to spend any money on development. We're just going to go to catalogs and buy off-the-shelf items and put them together. We'll call that the development or an integration. Let's just say by taking that approach of off-the-shelf components, that might result in a product or a system cost of about, say, $250. Now, if we go across the graph a little bit, let's say, well, what if we actually developed a piece rather than whether it be the hardware or another software element or whatever, to reduce the cost of the system? Then the overall cost of the system may come down from, if we spent, say, $7,500, it might come down to, $175, for instance. And of course, you can go across that graph and see that that relationship holds true. We all know that automotive companies, for instance, will spend millions and millions of dollars on non-recurring engineering to knock every fraction of a cent out of the design of that product. And so the real trick in this is knowing where you need to be on that curve. Because ultimately it's a matter of how budgets get allocated and spent. So we find that an important part of an IoT program and being able to make the proper decisions is to understand this relationship of non-recurring engineering and how it relates to product cost. So architecture. The architecture of an IoT system is critical, is absolutely critical in any system, but it is especially critical for the kind of systems that we're talking about here, a high mix, low volume IoT system. Because if the system is not properly architected, it makes it very difficult to be able to change out the individual pieces as you go along over time and try and upgrade it. So it's very important that when an architecture gets developed, that all the interfaces are properly documented in something called an interface control document or interface design specification. So for instance, if there's a Bluetooth low energy interface or something that is part of the system, that would need to be very well architected and designed and documented in a something like a GATT profile so that it can be understood over time and supported and maintained. Another thing to be thought about, of course, is fault tolerance of the architecture. Oftentimes, architectures get developed and they only anticipate the system, only under normal conditions. So how good the architecture is really also depends on how does it respond to off-normal conditions. And so a lot of times what will happen is a system gets architected, for instance, where there's a cloud component. And then if the cloud goes down, then the whole system goes down. And that can obviously result in a very undesirable operation. So that needs to be considered. Another thing to be considered is the distribution of functions. So sometimes it makes sense to do a lot of the processing right at the edge, right on the sensor, right close to the sensor. That might be because of timing considerations, perhaps a number of other factors. But with a good architecture and with a good vision, a long-term vision, it's possible to develop a lot of these elements so that they can be redeployed throughout the system. In other words, you could develop a chunk of code that might live on the cloud and take raw sensor data and do that processing on the cloud. But that same element could also be pushed down perhaps to a gateway or a mobile app for further flexibility. So these are some of the things that a good architecture will provide. What are some of the telltale signs of a poor architecture? We could probably make this list go on forever, open it up to questions and everybody could talk about it, but we just listed a few of them here. A poor architecture is one that typically is difficult to maintain. You make a little change over here and something pops out over there, or it affects more elements than you would like. A poor architecture, a system that has a poor architecture, typically requires a lot of extensive and expensive regression testing. So in theory, if you made a little change in this part of the system, if it was well designed and modular, then you would be able to minimize that regression testing. And another telltale sign of a poor architecture would be that it doesn't scale and it hasn't been anticipated to scale. So that's a sign. Some of the characteristics of a good architecture, on the other hand, would be, the system elements could easily be swapped or upgraded. So whether they're infrastructure components or gateway components or cloud providers or whatever it is, that with a good architecture, very quickly you can move from A to B. And so it may be that on your program, your IoT program, you say, we don't want to redevelop, say, a certain cloud component. We're going to go to a certain company that are able to provide all these services, to you for managing your data, displaying your data or whatever. And with a good architecture, you can use that component until it makes sense not to use it anymore. You might want to pull it in later downstream or whatever, but if you paint yourself into a corner early on through a poor architecture, it doesn't allow those kinds of decisions to be made. A longer life cycle is another aspect of a good architecture. Again, because it starts off with one set of components, but maybe 5-10 years down the line, all the components have been, traded out, and the only thing that's really surviving is the architecture and the interface definitions. Everything else has been upgraded in the process. And then another thing we listed there is, of course, is the system would be extensible as well. A good architecture allows you to be able to do things that you maybe didn't know exactly at the beginning that you wanted to do, but as you got more experience in everything with the benefits of the system, you want to do some other things with it. And a good architecture will allow you to extend the system. It's also important to understand that although I was just talking a little bit about system architecture, these architecture aspects apply to the individual hardware element design items, as well as the individual software elements wherever they are in the system. So architecture can include things like, physical components and how things plug together. So it's important to keep that in mind. Okay, so we're going to take a little transition now, and let's talk a little bit about what it takes to initiate a high mix, low volume IoT program. Let's talk a little bit about a subject near and dear to our hearts here at LogiSync, and that's hardware. So even a few years ago, when one wanted to take a wireless device, say a sensor, whether that was coming in over a Zigbee wireless network or a Wi-Fi network or whatever, and if you wanted to bring that sensor wirelessly into a system, it would oftentimes require multiple processors, multiple microcontrollers to do the job. So you might end up with a board that has 3 microcontrollers on it. The first microcontroller might talk out to the sensor network, whatever that is, and grab that data and manage that sensor data and get it into a host processor. That host processor then in turn might do some value-added processing on those sensors and then pass it off to another processor. It might be a Wi-Fi processor or some other communication means. And typically in the industry, the terms being thrown around for this is the sensor end is referred to as the south end of the application, and the networking end is referred to the north end. So over the last several years, a lot of exciting advances in technology have allowed us to combine these processing elements and make the job a little simpler than what it used to be. So rather than having to have a separate Zigbee processor and a separate host processor to drive it, these now have 32-bit RISC processors and everything in them, and they're very powerful. So you can not only perform the Zigbee interface function in the processor, but you can also program that processor with your own application. So many end devices have now become truly single chip solutions. And in a moment here, we'll show you what we mean by that, just how small and how inexpensive some of these wireless network interfaces can be for devices. Traditionally, when you wanted to build a processor design, the processor and all of its memory and other elements would be put on a base module, a CPU base board. And then, so all the high-tech stuff would go down on a base board. And then you would plug in a series of low-tech daughter boards. So as an organization, you can say, well, here's our standard processor module. And this division plugs these kinds of IO cards in, and this division plugs these IO cards in, and whatever. So that's kind of the way for a long, long time the industry was running. Again, high-tech baseboard, low-tech daughter boards. Well, a very important change has occurred and is occurring, and that's with the advent of system on modules, SOMs, and system in packages. You'll also hear the term core modules thrown around out there as well. So you can see on the right side of the chart, there are examples of those. The upper one happens to be a single chip solution. There's actually maybe multiple chips under that can, but it's basically looking like a single chip integrated module for providing Zigbee wireless interfaces. One of the advantages of buying a module like this rather than building your own, other than the cost, is you don't have to go through an FCC test. All the testing and everything has been done on this beforehand, so you can take credit for that in your own application, and it saves you time and money in getting to market. Below the Zigbee module there, you'll see what a typical system on module would look like. And so this is an example of all the high-tech, high-speed, there might be memory interfaces that are controlled impedance wiring and all of that. So by taking this kind of an approach, you leave that to others, and it's all on that module. And then more recently, we're seeing more and more of these system in package modules coming out. Octavo is one of the providers of those kinds of solutions. And it's really a logical extension of a system on module where they've really taken all those little components that you see in the middle picture and swept them all into a single package that you can install in manufacturing. Okay, so at this point, I think we're gonna switch over to show a few pieces of real hardware here, just to illustrate in a little more detail what we're talking about here. Okay, first I'd like to show, we were talking about just the size and the low cost of interfaces, equipment interfaces these days. This little part right here that I'm highlighting, that one little chip, that is a Bluetooth low energy interface. So you can put that part inside, equipment, sensors or whatever, and it's capable of communicating to gateways, cell phones and that kind of thing. These things are now, well under $10, fully capable of programming your application and everything. So that's how exciting this technology is these days. Some other examples of what we were talking about, that on a high mix, low volume kind of program. This particular box is associated with gas distribution valve monitoring. And this was a case where it was more of a software program than a hardware program. Because of the volumes, it didn't make sense to go design each of these components individually, because there might only be hundreds, perhaps thousands of these. So this is some development, some integration, and a lot of software. But this is an example what a typical high mix, low volume kind of product might look like. This device here, this is for the subsea drilling industry. It's another similar type of thing, a lower volume. It didn't make sense to go design this particular module custom. This is the CPU core module that's used on this, and that's all the high-tech stuff. And then we designed these base modules for it to go on to that customize it for that particular customer's applications. This is an example of a system that also is maybe a little more volume than some of these other systems, but again, it's a network system. There are parts of this system, not this part of it, that were purchased off the shelf. So this particular customer understood the elements of the system. They understood where their money was best spent. This is where the volume was. So they said, hey, let's spend the money on this element of the system, because that will increase our overall margins. Okay, so let's talk a little bit about some of the benefits of these modules and system in packages. First of all, it's obvious that it drastically reduced the cost, the risk, and the schedule for new products. One of the things with these new CPU designs is a lot of times they may take more than one spin to get it right. And most companies that are experienced in developing those kinds of modules understand that, and they built that right into the schedule. So by being able to go buy that particular cost element off the shelf, it sort of removes that element from the equation. Another thing, another benefit is there can be a huge reduction in the software lifecycle cost. Again, that requires a good architecture. So if you have a good system, hardware, and software architecture, then you can reap those kinds of benefits. But the code can be developed in a manner on that module so that it's not too close to the hardware. So ideally, what happens in 2 years or 3 years or whatever, when that module either goes out of production or a newer, more powerful one, becomes available, or even changing to a different manufacturer, that code then is not so directly tied to the hardware so that it can be picked up and moved to other platforms. The benefit of that is just astounding right across the entire life cycle that we talked about earlier. It's not just in the design, it's through all those life cycle steps, the testing and everything else, and the support. The modules in SIP approach, they also favorably affect the make versus buy decision. So not too long ago, an engineering team might be sitting around thinking about designing something that could be very important for them for their business model. But they may have thought, oh no, we would never want to go design that hardware because that'll be too expensive. That might be, 100,000 and this and that and the other. But with these modules and these SIPs available right now, it drastically reduces, the hardware cost. So the cost of ownership for a custom piece of hardware is a lot different now than what it was even just 2-3 years ago. And because of the lower cost, what tends to happen then is it enables applications that were previously unaffordable. So now if you get your cost down and everything, now it opens up the application space to areas that you wouldn't even consider before. One of the other nice things about the module and SIP approach is it doesn't preclude cost reduction through further integration. So it may be that you start off with one of those modules, and let's say, hey, your idea or your high mix, low volume program was a big hit, and now it's moved from high mix, low volume to a high volume kind of program. The nice thing about the modules is you could then design that module out of the system, move your software over, and because you've done a nice job at the system architecture, it supports that kind of a transition. And then you can drive towards the absolute lowest and cost optimized approach for the system. So the process for getting started. I think this first step is a very important one. And to make an honest assessment of where you really are. And there is quite a spectrum. At one end of the spectrum, there will be, you may be someone that says, you know what, we've not done anything with IoT at all. We know that there could potentially be benefits. We don't know what they are. Maybe there are, maybe there aren't. So you might kind of be at that end of things. And then the other end of the spectrum might be, you could be on your 4th generation of IoT deployments. So understanding where you are in that process, you meaning the organization, is a very important thing, because if you understand where you are, then you can very quickly look at, say, what did we learn from the past, if you have some past in the area, or take the time to really set out some clear goals about where you want to go in the future. Second step that's listed there in This often gets done, but it gets done in a manner that I think is just to kind of check a box. This needs to be real, and this is something that has to be really verified and corroborated with everybody in the organization to establish that business case and really tie it back to a return on investment. It's so easily to just start sending data everywhere, anywhere, and if there isn't a a clear case about understanding how that gets used, how it gets stored, how it gets disseminated, all of those kinds of things, then it can be tough. And I think that business case is something that will make sure that the program gets support at the highest levels of the organization because you tie it to an outcome. The third step there is to formalize the requirements. All of us who write requirements have a tendency sometimes to want to jump beyond the requirements and get right into the specifications. And you have to be very clinical in the process of separating requirements from specifications. So requirements are what it needs to do, and the specifications are going to be how it does it. When you commingle those two things, it can cause problems. And so if possible, to sort of make that a separate process is best. So once a formalized set of requirements are out there that respond to the ROI, and presumably when you have those requirements, you won't be doing meaningless things. Those requirements will be reviewed to the point where you say, we know exactly what the system is supposed to do and why. It doesn't have extra bells and whistles that don't respond to a particular need. A lot of tools for doing that kind of thing. Quality function deployment matrix, where you map features to functions. And if you have a lot of, or features to benefits, if you have a lot of features but not a lot of benefits, you might want to consider pulling some of those out. So once those requirements are laid out, then it's possible to synthesize some potential architectures. It may be that to meet a given set of requirements, there might be 4 ways to go about it, or 5 ways to go about it. It's important to identify those ways individually, specifically, put them on a trade-off table, make up a trade-off table, and then trade those architectures off against criteria that you've established within your organization. There will probably be technical criteria, and there will probably also be business criteria. So technical criteria will be, oh, well, we think we ought to choose this architecture because it supports 32 devices, and the other one only supports 16 or whatever. And, so you'll be making those kinds of decisions. In addition, you may be making business decisions. It might have to do with license costs and royalties and things like that. So all of these kinds of things get kind of shaken out during the process of the trade study. So once you trade off and select an architecture based on that weighted criteria, then it's really time to produce a program plan. And it's a good idea to obviously involve all the parties that are necessary of making that happen, making sure that there's a good responsibility matrix in place, that everybody understands what they're doing, by when, what tasks affect each other, just good straight up project management, and then sell that plan among all the participants and get their input. The last step that's listed there is to engage a systems engineering partner early, because you can see, hopefully through what we've been talking through here, is if systems engineering is brought in too late into the process, the die has already been cast, and it's very difficult to reap a lot of the life cycle benefits and everything that we're discussing here, unless that systems engineering is done right. And then it could, if it isn't, it could just kill the whole program, the whole, high mix, low volume program, because it won't be tenable. It will always be stuck in some kind of a state. So a few summarizing comments here before we open it up for questions. Clearly, the benefits of IoT are real. We see it all around us. You see it in systems all around us, but I think most exciting is there are a lot of systems that are happening that we don't see, that are going on, almost invisible to us. And these systems are hopefully, in most cases, making our lives better, increasing our quality of life, doing things to improve safety and security and all the other things that we're trying to do as we're trying to manage an increasingly complex society. So the benefits are out there and they are real. And today's technology, because of the advancements and things that we've talked about here in this presentation, you may have been sitting on the sidelines for quite some time thinking, I don't know that this IoT world is for us yet because it seems too daunting, seems too expensive or whatever. But that's where, companies like RBB and LogiSync are positioned to really be able to help you in that quest. The keys to a successful program, not surprisingly, I've said it over and over, the strong systems engineering and the architectures, choosing stable and demonstrated technologies. Everything moves so quickly in this world right now. It seems like as soon as you buy, chip version A and you get it soldered down to the board, then chip version B is out there. So it's very critical to choose, of course, technologies that aren't too bleeding edge, but also things that aren't too old and that are going to go obsolete on you. So those are critical decisions that have to be made. It's important to have an experienced team that's skilled in customizing these technologies. So it's not enough just to have great technology. You have to have the team that can put those technologies in motion and get them customized for your specific use and be able to integrate with your own internal capabilities, because the whole idea, of course, in any partner program is to have all the partners working at their highest and best use. And strong partners are an important part of that. And then lastly, having sound project management to pull together all the pieces of this and everything is what will give your program the best opportunity to succeed. So I'd like to thank all of you for attending here today. Hopefully you found the material here to be useful and thought-provoking a little bit. But what I will say, I guess, in closing here is I believe that we collectively are living during, in spite of the challenges, that we have, especially this year out there, I believe that we're living in a very, very exciting time. It's a time that we can really affect our environment. We can use this kind of technology to improve the water we drink, the air we breathe, the safety of transportation, and all kinds of things. And we as technologists and engineers are given a wider set of tools than we've ever had before. And it's very gratifying to be able to think through a complex problem and think through the system and the architecture, and then to be able to look out there in the market and say, wow, I have all the things I need to put that system together and make it a reality. And a lot of the things that we do today aren't really new. I mean, remote communications has been going on for a long time and things, but the way we can do it and the standards that are involved that help, cut the cost and the schedule of that, it's unprecedented. So we're very excited about building these kinds of systems. We hope you are too. And certainly if you need any assistance in doing that, RBB and LogiSync would be very happy to help you in that endeavor.